Henry, thank you, and I also want to thank you for letting me come here to Westland today. The talk is about 90 minutes, and try to hold your questions. If you have one, that's fine, but we're going to try to get through it in 90 minutes. The talk is 60 minutes, and then we're going to do some experiments that are going to take about 20 minutes or so. So I've been working at the Storm Prediction Center now for 22 years, and I've been in the Weather Service since 1994. So that makes about 30. And this talk is on high-end tornadogenesis. We're going to look at hypothesis, we're going to look at some observations, and then we're going to do some simulations. First, I want to make some statements. The first thing, in our quest to understand tornadogenesis, we should always use observations as our starting base. Model simulations play a supporting role to suggest to us what possibilities may or may not exist. Observations tell us what is actually happening at a certain level of detail. Model simulations show us possibilities, but almost always contain error. Analyzing radar data can involve both subjective and objective methods contrary to what is often believed. When we did the research project 2 years ago, we were using readouts from GR Analyst 2, and we're getting actual distances, measurements, and estimates of velocities, and reflectivities, and DBZs. So those are all somewhat objective measurements. There's a lot of subjectivity in radar, but we try to focus on the objective methods so we can make better conclusions. And then for understanding tornadogenesis, radar has been underutilized while model simulations have been overutilized, and that's just in my opinion. Cameron Nixon, who I'm working with at the Storm Prediction Center, also agrees with that assessment. Model simulations are important. They give us a good idea of what's possible, but we have to be careful. So for the Tornadogenesis project 2.5 years ago, we had focused on developing objective radar analysis methods using measurements to help us understand tornadogenesis. We looked at 208 cases examining EF3 to EF5 tornadoes. We wanted those tornadoes to be undisturbed when they developed, so we didn't want another tornado ongoing at the same time. To support our conclusions, we show the distributions with relatively large sample size, and we focus on example cases that support those distributions. You can tell somebody what a tornado might have done or what it might be doing or how it might have formed, but if you show them an actual case or you show them 4 or 5 cases, then they're going to believe you. They're more likely going to believe you. So for the Tornadogenesis project, we believe that tornadoes happen for a reason. There's a reason why they happen. The storm doesn't just get strong enough and then it just produces a tornado. There are a lot of different things, as Henry was alluding to, that happen to make a tornado, and they'll have to come together in the right way. They involve both supercell and environmental processes. So you see the supercell right here, but we have other things going on, other storms. We have maybe a boundary or maybe a localized enhancement of winds, and those all impact the storm as well. So we have environmental processes that we have to think about. If our research is on target, then we should achieve increased predictability with time. So this one is the 6-state supercell. It crossed 6 states on March 12, 2006. My friend Mark Darrow and fellow worker at SBC, his wife was in the plane and she was looking out the window taking a picture of this storm. And she could see the anvil here. We've tried to emulate. And the supercell, the flanking line would be to the left side of the picture where you see sort of the cumulus that's feeding up into the anvil. And you can see a hint of an overshooting top there. And so this is the supercell schematic that I put together 2 years ago. And what it attempts to do is to show you where all the different features are. The rear flank downdraft boundary, the RFDB, is in black. Right here it's this curved boundary. And then the forward flank downdraft boundary, which is more of a thermal and maybe a moisture boundary. There's not so much a wind shift a lot of times along it. Is it a boundary or not? Well, I believe it is. Then you have the inflow area, which is the area that Henry talked about, where you can actually see things really well for the storm. The mesocyclone would be the area that's turning right here. And then we have what we call the descending reflectivity core right here in light blue, to the south of the tornado wrapping around it. So this is looking downward from above a supercell. So you're looking down on the supercell. The forward flank downdraft that's interacting with the updraft is right in blue. The rear flank downdraft is in red, and the updraft region here is in brown with the tornado circled in purple. This is what it looks like on a radar view from looking at on a planar view. So you're looking at a radar scan at the lowest elevation angle. So we're making a cut approximately anywhere it can be from a few hundred feet above the ground to sometimes a couple thousand feet above the ground. And this is the Salyers-ville, Kentucky EF3 from the tornado outbreak on March 2nd, 2012. You see the rear flank downdraft area. Actually, the rear flank downdraft does include this whole area behind the boundary, which is in pink. But the real strong part of the RFD is where the hook is, and it's wrapping around the tornado. And then the forward flank downdraft, which also includes the entire core of the supercell extending off to the east. But the forward flank downdraft that might be involved in tornadogenesis just really generally right here along this gradient. And so the DRC in this one, would be the most prominent element of the DRC, although you could also extend it back into this area, but we're looking at the part that's interacting with the tornado. We're going to take a look at some examples, and before we look at the radar, this is a code that you need to remember when you're looking at the radar. The M stands for mesocyclone, the O stands for RFD occlusion. So the RFD is part of the downdraft which can surge outward or can move backward, depending on how strong the downdraft is within the RFD. The downdraft contains sometimes heavy rain, very large hail, and strong winds. Other times, it can be just outflow that surges out from the supercell. But when you see the RFD boundary bulge out and start to become curved, that's a sign that maybe the RFD is surging. And so when the RFD surges, then it moves often under the mesocyclone with a really well-organized supercell that will produce a tornado. You often see the RFD surge underneath the mesocyclone, and then a circulation develops near the ground, and that we call the RFD occlusion. There are other names for that. Some people call these internal RFD surges, but we have been focusing on the descending reflectivity core, which is here in purple. And then when you see T, of course, that means tornado. So the first case we're going to look at is June 18th, 2023, Bay Springs, Lewin, Mississippi, EF3 tornado. We were doing DRC analysis at the SBC. Matt Flournoy was my partner, and we were doing MD discussions. And I told Matt, since I'm training you today, you're going to do the MD discussions, and I'm going to do some DRC analysis. And if you need help, then I'll do some discussions as well. It was a somewhat localized tornado outbreak, and it gave me the opportunity to do some detailed analysis that I wouldn't have otherwise been able to do. So this is a planar view of the Bay Springs, Mississippi EF3. We actually anticipated this EF3 in advance because these storms were producing defined descending reflectivity cores in the rear flank downdraft area, and the RFDs were surging out, the forward flanks were organized, and we were just thinking that there was going to be an EF3. I diagnosed this storm in real time with the cross sections, and I was looking for the DRCs. And so what we're seeing here is the storm is about 20 minutes away from producing a tornado here. You see that the rear flank downdraft is this pendant that extends to the south-southwest of the storm. The mesocyclone is out ahead of it. The RFD boundary is actually between those two. I'll mark that on in a moment. But you can see the storm is moving east-southeast. And then the RFD occlusion develops right there. You see the O. And then on the next one, the tornado forms. Where's the DRC in this one? It's this little piece of higher reflectivity right in here. And if you look right here, you can see the nose of the DRC wrapping around the tornado. So let's look at how to do a cross-section to find a DRC. So there's the DRC that I just pointed out to you. That's at 2,500 feet above the ground. And so this is after the tornado has formed, but not very long after, just a few minutes after the tornado formed. So let's go back and find where is the reflectivity maximum in that developing hook. It's back to the west-northwest, several scans, and I'm up higher in elevation. So I'm up at 7,500 feet, so I've actually moved the scan up, and I'm tilting it up and looking up higher in the storm. So I've got the cross-section lined up right along these two areas where the reflectivity is maximized. And if you notice, even if you go all the way back, it follows that area of higher reflectivity. So this is the cross-section. We lined up the cross-section along the path of the pendant, and then later on the hook, and the development of the DRC. So this is the cross-section. So we have just taken a cross-section along that path, and one thing to keep in mind is that the radar is scanning. So this is not just a once cross-section, like right on that time. This is a combination of different times all put together. So what are we looking for? We see that it appears that this is a cell that's developing just behind the pendant. And so we have the pendant of the supercell and then the blow off here. And so we have what appears to be a cell developing behind the pendant of the supercell, and it approaches the flanking line, and there's a cell merger there. And so we looked at 208 storms, and in these cases, we started to notice that the DRC was coming out of the cell merger. And so see the DRC gradually drops down to the ground, and then we have the tornado that forms. So this one forms and then descends. And so what I've done here is I've marked the leading edge. I went on velocity, we actually looked at where is the DRC wedge front. So there's air that's coming in this core and coming down. And so I marked the location of that. And so if we look at the velocity, so there's two ways the DRC can impact the storm for a tornado. The first way is that it comes down and then it hits the RFD occlusion and the tornado spins up. There's also another way we've identified where there's a lot of precipitation aloft, which is called the bounded weak Egger region. So you have a lot of reflectivity aloft that the mesocyclone is supporting. The DRC can come in and merge, and then the supercell will unload that big area of heavy precipitation. All the hydrometeors come down all at once, and you get a big surge downward. Then the tornado forms. So there's different ways that this can happen. Let's watch and see what happens with this one. It's not real evident where the DRC is, but you can see where I marked the wedge front based on the reflectivity, velocity. But look what happens here. So we're about to the meso, which is where these higher winds are. The DRC is coming in. Now watch what happens when the DRC hits this area where the stronger winds are aloft, they drop. And so let's follow that orange, the area of higher winds. So right when the DRC wedge front got there, the high winds descend. And so in observations, we've seen this happen, where you get a really strong downward area that hits the ground and spreads out, and then the tornado will form. Now the tornado is upward motion, so we're not saying that there's any real downward motion in the tornado itself. And the tornado will generally develop from the ground upward, or it will develop within a column all at once. It just depends on how the storm is organized. So in a supercell, like the Simulatiion, Kentucky case, we typically get an upward motion in this area, and a high pressure area will be present in the rear flank downdraft. And the motion will kind of be around that high in an anticyclonic manner. But in addition to that, we get a lot of convergence in this area. And that's where we're seeing cell mergers that are often developing and helping the DRC to initiate. So here's the cell. There's two cells here. One I've marked toward the top and one toward the middle. You can see where it is relative to mesocyclone. Watch these two cells.
They merge.
So they merge. Then I've got the DRC position there, and that's at 7,600 feet. Now I've lowered the elevation angle. We're at 4,400 feet there. 3,000 feet. Now the top of the DRC is visible as it hits the ground, and the tornado starts to wrap around the RFD collision, and the tornado begins. So we're seeing that in this case, it looked like this cell merger was really important. And so what I like to describe it as is, if you play pool and you have two balls that are coming together, and the one that's moving faster will sort of deflect the one that's not. And so a cell merger might have two downdrafts that collide together. The stronger cell actually may start to push the weaker cell or the weaker core downward. So this is a hypothesis. We know that if you have two downdrafts and they come together, you're probably going to get a stronger downdraft because you're binding them together, right? So that's the idea here. And the timing of this is really important. Now I've marked the DRC, the cell merger, and the mesocyclone here. And this is the smallest component of the DRC, although you might actually consider this, all of this, the DRC here, but this is the smallest component, and that's gonna be what interacts with the rotation near the ground. So the RFD occlusion there in O. Now see the RFD boundary? Look what happens when it crosses underneath the meso. The RFD occlusion starts to develop. So there is downward motion in and around this area. And so when we have a mesocyclone like this, when the downward motion gets to the mesocyclone, some of that air that's going up starts to go down a little bit, and it helps to kind of sort of drag that rotation down toward the ground. And so when we see the nose of the DRC pass by the rotation at the ground, that's when the tornado develops in this case. And so I've marked the DRC here. What I'm gonna do is I'm gonna turn the DRC so that I'm gonna just turn it. So now we see where the tornado is relative to the DRC location. And this is determined with continuity. So it's good to look at 4 or 5 scans in a row and work it all out. Don't just use one scan. You work it all out and look up. And that's what a radar operator has to do. You need to have continuity both temporally and spatially. So the second one we're going to look at is the Simulatiion case that we looked at earlier. This one here occurred on a major tornado outbreak in 2012. So this one here had an RFD surge that started right there. But if you look, there was something that happened. The flanking line sort of flared up. Then the RFD surge stalled and actually stopped. And we had a second RFD surge.
Okay.
And that one was associated with the DRC. And before we go on, do you see the extension out toward the west here? Now watch 2 scans later. See the extension out to the east. Well, that's the DRC coming in. And it's hard to recognize these things. I didn't see this during the original study. This case puzzled me. But sometimes it's better to put things down and then pick them up later. And so we had 2 surges with this one. Now what happened, remember the Bay Springs case that you just saw? There were 2 cells, one north, one south. Watch what happens. So so we see the merger again. And then the DRC comes out of it, and the tornado wraps around the tornado. And it's very well timed. This little C here was a RFD boundary circulation that lasted for 2 scans, but it didn't produce a tornado that we know of. But again, the timing here is really important. You know, we see the merger, and then the DRC, and then the tornado. So this is what we're seeing in a lot of these high-end tornadoes. And when the 5s, this is what you generally see. With the 4s also. With the 3s, you're starting to lose some of this. You see this kind of thing with some of the 3s, but with others, not as distinct or defined. So when we mark where the position of the DRC was, there's the tornado position and the DRC. So this one is a little bit more in front, but again, it's behind the DRC. And so what we hypothesize is that the DRC is blocking the flow and focusing the inflow into a smaller area, which then causes the pressure to really drop, because the mesocyclone is evacuating air aloft, and the air that's coming in to replace it down below is not as much as before. So the pressure has to drop. So when you evacuate a lot of air aloft and you can't replace it below, the pressure will drop, and then the circulation will start to intensify. So this is what we saw after 50 storms were analyzed. This was done after the 50th storm. I drew the time series here of what I was seeing in the cases. And you generally see an RFD surge, then it surges toward the forward flank and you get this inflow channel which forms, and then the tornado will form as the organization increases. We looked at the surge of the RFD, it was very important, and we generally saw an RFD surge in all the cases that we looked at. Partly the RFD surge is a response to a stronger rotation, but we found that the cell mergers were really important in supporting the RFD surge as well. We looked at the organization of the inflow channel, the development of the RFD occlusion, cell mergers, and the descending reflectivity core. Cell mergers weren't even on the radar when the study began. Weren't even thinking about them. The descending reflectivity core was sort of a second thought. It was like, well, maybe we'll just take a look. So we did find that cell mergers and DRCs. The DRCs were the strongest relationship that we found to the beginning of the tornado. So all of them had an RFD surge, and it tended to be significantly reduce the window from which the inflow must pass. So the inflow window shrunk as the RFD surge moved out, and it was usually relatively long in duration, greater than 15 minutes in length. So where did the tornadoes in our database form relative to the RFD boundary? the average location was almost 2 miles to the west of the boundary. So significantly west of the boundary. There were some cases that formed in the northeast quadrant of the RFD close to the boundary itself. We can see that there were 7 cases that formed either on or very near the RFD boundary. And there is vorticity that can be created along the RFD boundary. We've seen many rotations develop in a vertical nature. There's some new work that's being done suggesting that there's vorticity that can be turned and interact with the boundary as well. And that is another way you can get tornadogenesis. But the predominant way that we found in our study was that there's something in the the rear flank down breath that is helping tornadoes to get going. And that is the DRC. And then the cell mergers are helping those DRCs to initiate. This is where the cell mergers that we had for 77 cases relative to dependent. Why did I do 208 cases? Because if you notice, I've got everything scaled to the supercells. And so there was a lot of work here. I did a lot of the work in the 6 months preceding the conference, and I was running out of time. So I did the best I could. And so we have 77 cases there, but we still got a very strong signal that the cell mergers were occurring on the backside of the pendant. Closer to the tornado, the cell mergers tend to be just south of the hook. And so we have 119 cases there, because that's cell merger 2 and 3. And so the cell mergers were done for all 208 cases, but that graphic was only done for just a subset. So DRCs, RFD surges, and cell mergers were done for all 208 cases independently at different times. The cell mergers were done a year and a half before the DRCs were done, and the RFD surge was done before that. So I was not thinking about anything related to how they work together. Totally independent. And then when we broke down the distributions of the timing, it looks like that the cell merger was generally the first thing that happened. Then the RFD surge would happen, say, second if it was closer to the time of the tornado, and then third if it was further away from the tornado. So generally your cell merger was first, then the DRC and the RFD surge followed shortly after. And so when we're looking at a cross section, we are actually combining lots of planar views together to get the cross section. So what happens is, since the storm is moving, this one happened to be moving at about 50 to 55 miles per hour, it will actually take time for it to collect the data. So when you see a cross section, it actually should look more like this, because as the storm moves, it's tilting that data and putting that data together. So instead of this, that's more like reality. And so where's the DRC on this day? You see it outlined in white. And so that would be more like reality. Now, is it easier to see it if it's tilted? I think so. So that's actually an advantage. But you have to remember